I'm going to upload the meeting recording afterwards on Moodle as we did so far, or as I did so far. Okay. All right, so good morning, everybody, once again. I hope you had a good week and that you found yourself easy to come to this meeting today. As we said also, or as I said the last time at the classroom, I'm actually traveling due to business. So these 3 weeks, I'm not going to be in Munich. Therefore, we have the meeting today virtually, and next week I'm unfortunately on a conference, so no chance to give a lecture or a practical lab session, as we call it. Therefore, this lab session is going to be we're not going to run it or conduct it place on a Wednesday, probably. I'll let you know, or Friday. Not 100% sure yet. It depends on the depends on how my schedule is for that week. But I'm gonna inform you on due time, and you're gonna get an email as usual, an announcement from within Moodle, alongside with the exercise. So, for this week, we are concerned with the Timoshenko bean. You probably already seen that I uploaded some information on Moodle. That's the week we are, or let me see real quick, I'm in the right place here. Yep. So that was from the past week, basically. And you were expected to actually watch the recording. Hopefully you did that. And using the information in the recording, as well as the live script that I provided you with in the frame of the courseware, you should have been able, hopefully, to solve the exercises that I have underneath here. So let me see what I have here. This file here probably shouldn't be here. I just realized now, set of exercise basis functions. No, okay. So this has to do with the ordering of the base function. I'm going to talk real quick also about it because it might be useful. So firstly, we have the lecture notes as well. If you want to see the equations written form, we're going to talk about them. And the other thing that I provided here is called the note on the basis functions ordering. Well, this is, yeah, okay. This is more relevant for the next lecture that has to do with the rise and middling plate. So you know how we, in the courseware, how the basis, how the nodes and the basis functions are sorted for a two-dimensional element, because for a one-dimensional element is not straightforward. It's just like a one-dimensional entity, geometrically speaking, whereas the two-dimensional meshes or like elements are, they need some particular ordering, and this is what I wanted to elaborate here. But this is not the right place where I put it here, so I'm gonna have to move it to the next week, basically. Yeah, it doesn't matter actually. So let me see. Okay, so we have those two exercises. As I said, you will have time until the 9th of May to solve them, and that's because I put the practical lab session on this Friday. It was on a Wednesday, and plus we're not going to have a practical lab session next week because of the business trip that I'm on. So I gave you a little bit more time to elaborate those exercises. I think they might be a little bit more elaborate than the ones we've seen so far with the basic functions. These are a little bit more, as the course progresses, the exercises and the content is also getting a little bit more interesting. So hopefully you also see the same. And I'm going to actually open them in 2 new tabs. Good. So you may have noticed already on those exercises that the first one has to do with the linear discretization. So two noded linear elements here, it's written. So we talk about using two noded linear elements to solve numerically the Timoshenko beam, we call it boundary value problem. Whereas in the second exercise, you are working with the 3-noded quadratic elements. MS is provided as well underneath. And yeah, those are the 2 exercises that we had to work on. And I actually had a quick look on the statistics today morning. Let's have a look together. It looks like problem and didn't try it at all. Hopefully, after today's practical lab session and questions that we may answer here, you may be in a better position to actually try to solve them. And yeah, I just wanted to also look at the individual solutions. Maybe just take an example. First one, to see how things are doing here. So the colleague here managed to go up to the integrand, like getting the integrand of the stiffness matrix at the element 6. And there is an issue here with the load vector. We can see what was the solution provided here. All right, so we asked for the load vector at element 6 or 7. Let me see. So hopefully, question 7. Is at element 4 from where I can tell here. Hope I'm not wrong here. Let me go back to the solution. Six, okay. I'm not sure if that's a typo. Probably that's a typo here. I need to check it up because from what I can tell here, I asked you to compute the stiffness matrix at the element 7, but here it's written 6, so I bet that's probably like a typo from my side. I'm sorry for that. I need to correct this. I will note it down. But nevertheless, here we got, like, the colleague got it right up to the computation of the integrand for the stiffness matrix itself, which is not a surprise. So we have the B operator matrix, we transpose that, then we multiply that with the material matrix, and then again with the same B operator matrix, and that's pretty much it. So could somebody say, explain why is the stiffness matrix a function of the parametric space Xi? What is the reason for that? You can also type on the chat. That's if you prefer. Just to get things going and like to, you know, wake up already slowly. I need to find what is the chat now. Here it is. Okay. So the question is again, why is the stiffness matrix a function of Xi? What is the reason? Answer on why is this? Why is it? Because we need to integrate on the physical space, meaning in the X space, but the stiffness matrix here, it seems to be a function of Xi. What is the reason for that? Please don't be shy. Use the chat to answer the question. Okay, we already have some answers on the chat. I'm sure. Thank you very much for this. So one answer says the doves are described in the parametric space. When you say the doves, are we talking about the basically when we say doves, degrees of freedom? We talk about the individual solutions on the nodes, right? Nodal solutions. And this is basically, if I go back to the courseware, we will see. Let me see where I should go now. Oh, it's a little node, so I'm going to open that one up. So you station, and that's the beta, right? in each node has those two degrees of freedom. From what I can tell here, the degrees of freedom are defined on the physical space. They are not like beta and W are not described on the parametric space, or well, they're described with the help of the parametric space, which means that the beta is a function of psi, and oops, I lost it now. Sorry. Let's try that again. So in each node we have a vertical deflection and a cross-sectional rotation, and I'm trying not a rotation to get it right. And so that's going to be a beta of. I'm sorry, I missed it again. Beta. You get the point. Sorry, it's hard to use without an iPad. It's actually hard to type. But no, the degrees of freedom are not described in the physical space, on the parametric space. They're described on the physical space with the help of the parametric space. The second answer is because the colleague says maybe because the different DOFs depend on the location. We talk a lot about DOFs here, and I want to make sure that we are in the same page. So I'm going to open the PDF. I think it's easier. I have to scroll down to find the formulation. I think, let's see, where's the discretization? So it's here. There we go. So, all right, you may have already seen though this equation here, right? This equation is very important because this tells us that all right, so this has here a W and a beta. And a beta like this. So that's why it's a vector, because it has like both the vertical deflections and the cross-sectional rotations, right? And that's now when we discretize that, we have like the discrete form of that, which is UH, and then we have the basis functions matrix times the nodal solution vector. And this is exactly what we call here DOFs. So those are the DOFs. As you can see, the DOFs are not space dependent because those are scalar values at each node. So the DOFs themselves, they don't depend on either the parametric space or the physical space. There are some scalar values that are defined on the nodes. But the solution vector itself, it is a function, and especially the discrete solution vector, so this one here, it is actually a, I'm going to type it, I missed again, sorry. It's very hard to change like the alphabet here. Nevertheless, I want to say that this U is a function of psi, indeed. So that's right, in the sense, but that's the solution itself, which is both the vertical deflection and the cross-sectional rotation together. That's why it's a vector. That's why it's bold-faced. However, this part here, we have the basis function matrix, which is, now let's see, n of psi. So that, you see the dependence on psi already. And then we have the d's, and the d's are actually constant, right? They're dependent on the nodes. And another colleague says here, it will be applicable for any element. Actually, yeah, this is not really the reason why the stiffness matrix is a function of psi. But I mean, hopefully you can already see here that, and if you recall, from the recording and the lecture notes, what is happening here is the following, that we have the B operator matrix, right? Which is the constituent to construct the stiffness matrix. And the B operator matrix contains nothing else but the derivatives of the basis functions. And the derivatives of the basis functions, in turn, are functions of the parametric space. So meaning the n's are function of psi. And you see that here, right? Since we have the B operator matrix, which is a function of the derivatives of the basis functions, we expect the B operator matrix itself to also be a dependent on psi. And since the B operator matrix is also dependent on psi, and we know that the stiffness matrix is equal to the B operator transpose times the C, the material matrix times B operator, right? That's the integrand, by the way. It's not the stiffness matrix. We need to integrate that. We see that the K is going to be also a function of psi. So conclusively, what we say is that B, or the integrand of the stiffness matrix, is a function of psi because the B operator is a function of psi. And that's so because the B operator matrix is a function of the derivatives of the shape function matrix, and the shape functions are defined on the parametric space psi. Oh, I'm really sorry. A colleague says that you lost me for some time. I'm really sorry for that. I hope everybody can hear me well now. I can definitely repeat what I said. Good. It's good. Thanks for letting me know. Please let me know anytime you are losing the the voice, or I don't know, the internet connection gets interrupted, because otherwise I don't know how that this is happening. All right. So let's talk about B again. It is important to keep in mind those equations here, right? You see here, those are the linear shape functions. So we have, like we've seen those functions before. We have n1 and n2, and just for putting everything into a perspective, those are these functions, right? You see, these are. Let me put them on the side here. So the n1 is this one here, whereas the n2 is this one here, right? And you see them now with the red color and the blue color, and those. I'm gonna try to answer now the question of what is B. I just want to start from the beginning. We have the basis functions that are needed in order to discretize the field, and those are the two functions for the linear case. And now we are using those two functions to interpolate the field or discretize it. So I'm gonna scroll down here. I think it's better written on my. Right hand side, you see what is written on the PDF, and on the left side is what you see on the live script. It's basically the psi and the W and the betas are described by means of the shape functions here. So the NIs. What I've written here, it's a little bit confusing, so I will go ahead and correct it. So here, the W is not a function of X, but rather of psi, and that's so because the N's are also functions of psi, right? So we have the beta is also a function of psi, and N is also a function of psi here. You see this here. And that's now, if we collect those two into a vector, so I'll make a vector here like this and put them together in a vector, we obtain that expression in the boldface here, U boldface. The B operator matrix now, let's see if I have it written somewhere here. And let me talk a little bit also about the live script here, because I think it's useful. You will see that in the computation of the master stiffness matrix for the two-noded linear mesh, or even for the three-noded quadratic mesh, there is a function which is called compute element stiffness matrix and force vector Timoshenko beam. Now, this is a local function into the script. So if you actually right-click on that, maybe I should zoom in a little bit so that you hopefully see it better. So if I actually go ahead and I zoomed in too much, doesn't matter, and you say open compute stiffness matrix and so on and so forth, it will bring you down on the appendix of the script, and you will see the function down here. And here, it is basically written exactly what the function is doing. And answering the question of what is the B operator, or what is the B matrix, which is written on the chat, the B matrix is actually nothing else but this here. All right, so that's the B transpose, and this part here, I'm gonna use blue, is the B itself. So what do you see here? You see that the B operator matrix contains derivatives of the basis functions with respect to the physical space, not the parametric space, and also basis functions themselves. So we are adding here the basis functions, the derivatives of the basis functions together with themselves, right? So that's important to keep in mind. Pavan, I'm not. Is it clear what the B operator matrix is, or do you have any questions on that more? Does this answer the question on the chat? All right, great. Good. So having the B operator matrix, you see, it's actually straightforward afterwards to compute the stiffness matrix. It's not a big deal. So if you have the B operator matrix, then you can simply go ahead and do what I wrote before, which is B transpose times the material matrix times B. And of course, we need to integrate that. So we need an integral here over the physical space. And of course, we are actually doing all this in the element level because as we said the last time, the base functions are piecewise continuous functions. So you cannot evaluate this integral at once for all the elements. It has to be evaluated for each element. Hopefully that makes sense. So if you recall, we have a mesh, which is a linear mesh. So we have, like, let's say here we have 3 nodes, x1, x2, and x3. And let's say that we have element 1 and element 2. This matrix here, this integral has to be evaluated for each element separately. And that is so because our basis functions are not C infinity continuous throughout the whole space. They're just C infinity within each element. This is quite important. I would really like that you understand this, because I think this is a question that may easily arise when you're studying finite element analysis, is why are we evaluating the integrals per element and not at once for all the elements? And I hope the answer here is clear enough, because our basis functions, and in turn the derivatives of the basis functions, and in turn the B operator matrices, are not fully continuous throughout the whole space. They're just continuous within each element. And we can only perform numerical integration at domains where the base functions are actually C infinity continuous. If they are less than C infinity continuous, we cannot perform integration. That's the answer here. Is there any question on the construction of the B operator matrix and why we integrate it along each element? Is there something that you would like to know more? Okay, hopefully this is clear. What did I want to say now? I think this is a very interesting function here, and I would like you to take a moment and read it through, understand what's happening here. It's not hard at all, actually. But let us go real quick through together, and please ask me if you have any questions. Just unmute yourselves. You're more than welcome, or just type a message on the chat as you prefer. I think it's easier if you unmute yourselves, but as you feel more comfortable. So you may see here that I'm using a lot of the symbolic math, which is very useful because it's easy to formulate mathematical expressions without the need of having discrete matrices and discrete vectors and whatever. It's actually a little bit more intuitive, I would say. Therefore, what you can do also alongside with me, you can place a breakpoint on 202 if you have the courseware open on your side, and I would recommend you to actually navigate back. Actually, you can go all the way up to the script, and from this table of contents, you can actually click on the, let's see, master stiffness matrix and load vector for the 2 noded linear elements. So if you click on this hyperlink here, it will just bring you to the right place. And here, it's actually the place where we are performing the integration for the computation of the master stiffness matrix. So the thing is that, and probably you already know that from the introduction to finite elements, but I may repeat myself real quick here because I think it might be useful. We are actually computing stiffness matrices. So let's say the K1, the K2, the K3, and so on and so forth. And afterwards, we want to bring all those together in the master stiffness matrix K, right? So we want to actually get all these matrices into the master stiffness matrix. Can somebody please tell me on the chat, how do we do this? What is the process of doing that to bring each individual stiffness matrix into the master stiffness matrix? Or please feel free to unmute yourselves and just tell me what you think. What is the constituent assembly? Fabian is saying assembly. Very good, excellent. Can you please elaborate more on the assembly? What is the what do we need exactly for the assembly? Anybody else can answer, not only Fabian. So anybody wants, please type on the chat. Let's make it collaborative here. So assembly is the right word, of course. We need to assemble to the global stiffness matrix. But how do we do the assembly? That's what is interesting here.
We need to transform it.
Thank you, Zach. Transform it. Could you please elaborate a little bit more on that? What do you mean by transform it? Yes, please. Zach, can you please explain me first the transform it, and then I will go to the chat again.
Yeah, like the element stiffness matrix is in a particular like space, and we need to transform it to the global space.
Okay, that's a very good point. Thank you, Isaac. Thank you for bringing it up. This is very important because I think you are correlating it now to the truss elements from the introduction to finite elements, where the stiffness matrix is constructed on a local coordinate system, and then you transform it to the global coordinate system, right? Probably this is what you're referring to. Please correct me if I'm wrong, but that's my understanding.
Yeah.
Okay, great. This is not that, but it's great that you brought it up because it's a point of confusion. But thank you very much for bringing it up. But it's not that. So let me just try to explain. There is a lot of notions here, so it's actually a lot of confusing things. It's good that we put things in order. Let me please try to answer first to what Isaac said, and then I will go to the chat to discuss a little bit the other comments that are added there. So in the introduction to finite elements, you had a truss system. For those of you that actually took the introduction to finite elements, maybe some of you already didn't take that, so please bear with me right now. You had like a truss system, right? So there was like, let me just see how to do this. So there was like a truss system where you had, let's say, 2 trusses or whatever you want to have, and nodes here. And you see that the trusses here are actually defined on a Cartesian system, which is like a XY, right? Because it's a 2-dimensional Cartesian system. And you were actually, I'm going to use red color, you were constructing the stiffness matrix in really such a space here. So that was in a 1-dimensional space, right? Side, whatever. And you had like the task here, and Isaac is right. And I don't like Xi actually. I'll change that. I don't like this. So because it's not really Xi. This is like, let's call it X hat. Okay. Now the thing is that element in this is really a different coordinate system. Okay. It's not another space. Isaac, I hope I try to explain it. Please interrupt me if it's something confusing. So this is not another parametric space. So it's not that you have, let's say, let's use blue. It's not that we have here that X is equal to X of X hat, or that Y is equal to Y hat. That would be a parametrization, is what we've seen so far. But that's not the case. There is no such a dependence, right? It's really 2 different coordinate systems. I know this might sound really out of the sky, and I want to really put things in perspective, and you understand that. So it's different talking about a space and different talking about a coordinate system. These are not necessarily the same things, all right? So a coordinate system is like the Cartesian coordinate system. A parametric space is typically it's provided typically by a parametric description of a geometry. And this, what you learn in the introduction to finite element methods or finite element methods 1, it doesn't have to do with parametrization. So you don't have a parametric description of your geometry. Okay, I hope that's clear. You don't have a parametric description of the geometry. You have 2 different coordinate systems, and you want to transform from the one to the other. Isaac, what do you think about this answer?
Yeah, that makes sense.
All right, great, thank you. So that's a great point. Thank you very much for bringing it up, because it is confusing, right? Now I'm in this course, in the advanced finite element methods, we're talking about beams and plates. We are not going to do any coordinate transformation. So our elements are defined directly on the physical space, meaning, sorry, I said space, in the Cartesian coordinate system, and that's it. like what we do afterwards when we describe the element parametrically, we don't do a coordinate transformation. We have a parametrization, which is something else. It's what we've seen before, that X depends on Xi and Y depends on Xi, and so on and so forth. So, but that was a great question, because as I said before, there is a lot of different notions in the finite element analysis that, they might seem interdependent, and they may cause a lot of confusion. And my hope is that in this course, we eliminate a lot of this confusion as well. All right, let me go to the chat now. There is some message on the chat. And let's see what we have here. Okay, so Finlay said the right thing. Here we have the so-called element freedom tables. So if we have if we have a set of matrices here, K1, K2, K3, and so on and so forth, and we want to assemble this all into the master stiffness matrix K, we need the element freedom tables. I'm going to write it here. So we have the EFTs, we call them 1. Then we have here EFT3 and EFT2 actually in the middle. So we are adding all these element freedom tables. We are not adding them, sorry. You are using them to tell us where to put each entry from this element stiffness matrices into the global stiffness matrix. Important thing. Now, you've done that. Back to the question that Isaac posted before. You've done that also in the finite element analysis 1. But in the finite element analysis 1, where you had trust system, as Isaac system to the global coordinate system, and afterwards use the element freedom tables to construct the master stiffness matrix. So you had 2 steps. What I'm teaching here in the frame of this course, you don't need to do any coordinate transformation. It's just straight computing the stiffness matrix in the element level, and then using the element freedom table, you put it directly on the stiffness matrix. So there is no coordinate transformation here. Hopefully that makes sense. We need Eduardo says we need to evaluate the number of the number of each element. So this is not very clear to me, Eduardo. You can actually try to explain to me what you mean there. We need the number of each element. Maybe you mean the number of degrees of freedom or so. I'm not sure. Please feel free to yeah.
Exactly that.
Okay.
Table actually. Yep.
Great. Thank you very much. So indeed, you need the number of the degrees of freedom at each element. Obviously, that's really very correct. And using that, actually, you can construct the element freedom tables that was said before by Finlay. And using those, you can actually, take what is the element freedom table actually. But before we answer this question, I want to finish the chat here. Shurav is saying to evaluate primary parameters in whole domain of the beam. I think this is answering the question that I posed before about the element freedom tables. Shurav, also, I'm not 100% sure what you mean by to evaluate primary parameters in whole domain of the beam. Could you please elaborate on that? Degrees of freedom. Okay, great. Thank you. So yes, degrees of freedom are very important for the construction of the element freedom table. We will see what and how this works. Gabriel is saying we need to know which of the nodes in the parametric space are related to which node in the physical space. Gabriel, I think this goes back to the question of Isaac. The thing is, like, we don't have a coordinate transformation, so our degrees of freedom, they really just live in one space. They don't have more spaces. But I know that's a pain point, so that's a confusion. And I had it also, of course. Everybody has it. Or if you go from the finite element methods once to the advanced finite element methods where we don't do any coordinate transformation, is very confusing. We don't have actually another set of degrees of freedom that are in another coordinate system. We have only one coordinate system. This is the X, Y, basically. And we don't need to do any transformation. All right. We can actually really go into depth on that if it's confusing. Gabriel, would you like to tell me whether these answers, the answer that I provided to actually Isaac before helped you to understand that there is no coordinate transformation needed, or is there any follow-up on that? I'd like to clarify.
Yeah, I meant that we have to know which of the nodes in the parametric space is related to the physical space, and we only from that basis find out where we have to put the entries from the stiffness matrix we calculated in the global stiffness matrix. So we just put it in the right spaces and don't do further calculations on the entries.
That's a correct answer. Thank you very much. That's right. That's right. That's very right. So very correct. That's correct. So let me just build up on that, on what Gabriel said, because I think that's interesting. So let's say that we have a stiffness matrix. Where is it here? If we have a stiffness matrix here, local one, right? So I'm gonna say K, I don't know, KE or whatever, and that's equal to. I'm gonna try to type a matrix here if I manage to do that. All right, so let's say that this has some entries, right? And please, I will make it abstract. So it doesn't have to do now with the beam or the plate or whatever. It's very abstract. So let's say this has an entry K1, an entry K2, and I have to put also an E here. A K entry, I don't know. Well, I would like to call that around 1, 1 actually, and this is going to be the 1, 2, and this is going to be the 2, 1, and this is going to be the 2, 2. And let's say that we have now an element freedom table here. How to type this one here, which is equal to, let me think, I will say 3, 4, okay, 3, 7 or something. Can somebody please unmute themselves and tell me what does that actually mean? All right, so we have an element with an element stiffness matrix K11, K12, K21, and K22. It's like only 4 entries. So we have actually, let's say, what kind of a stiffness matrix is that actually? So we have 1 degree of freedom per node. If it's a 2-noded element, this is just like a 1 degree of freedom per node, so a truss or something. And we have here the element freedom table that says 3, 7. Can somebody unmute themselves and or type on the chat as well if you want, and tell me what does that mean? How do I translate that? And I'm gonna make a mesh also here. This is gonna be the node 1, and this is here the node 3, and this is the node 7. Can somebody tell me what does that mean for the assembly actually phase? How would we now go about assembling that element into the global stiffness matrix? And what about like the size of the element freedom table? Now the size of the element freedom table here is 2, right? It has 2 entries. Could it have more than 2 entries? Could it be 5 or something in this particular case? Let's start with this question. Actually, I think that's interesting. Why is the size of that element freedom table 2? Why is it a vector of 2 by 1? Sorry, it's not 2 by 1. It's a 1 by 2. Why is it a vector 1 by 2 and not 1 by 4, not 1 by 5? What is the size of the element freedom table? Anybody? Volunteers? Say something. There are no wrong answers as usual. Please feel free to say whatever you think.
Maybe because we have to have 2 nodes to be related from the one space to the other.
Exactly. Thank you very much, Gabriel. That's exactly that. So the size of the element freedom table is literally either the number of the rows or the number of the columns. So obviously, I mean, for me, it's obvious now because of that. I'm doing that for many years. But the stiffness matrix has the same number of rows and the same number of columns. That's expected because in both sides we have the number of the degrees of freedom. So it doesn't matter how many rows you have here. You are going to have, this is the number of the degrees of freedom, num dofs per element, right? So this is not the global one. And the same thing holds for the number of sorry, that was the number of the columns, and that's also the number of the rows is the same. Okay, as Gabriel said. That's right. So we have here 2 degrees of freedom per element, and that's why the element freedom table here has 2 entries. Perfect. All right. So Alexis is saying on the chat that the nodes which the element influences. Perfect. That's the great answer. Thank you so much. So it means actually that if my stiffness matrix is, I'm going to blue color again. Let's say K is my global stiffness matrix. This is not a nice place here. Sorry. You see, without an iPad, it's really hard now to try to type here. But I'm sorry for this again. Let's say this is the global stiffness matrix K. We are literally going to go to place this the K1 the K11, or let's take the K21. It's more interesting. So red. The K21 here, the K21 entry is going to be placed at the row 3 and column 7. So we just have to find this one in the global matrix. And at this location here, we're going to place the K21. That's how the assembly works. And this is exactly what Alexis said in the chat. It really tells us which nodes in the global, not the global, because global might sound confusing, in the master stiffness matrix, in the whole system, are being affected by this particular element, right? We have 2 different numberings, actually. It's really an artificial thing here. We have numberings for the local element, which is like 1, 2, 3, 4, whatever, as you see here. And they're sequential, right? So they start from 1 and they go to the number of the nodes per element. And then we have also the numberings of the global stiffness matrix, which are different, right? Because the global has more nodes, right? And now we need to answer ourselves, where do these entries go on the global level, in the global stiffness matrix? And that's, to answer this question, we need the element freedom table. All right, I hope that's clear. Please unmute yourselves and ask me if you have any questions and this is not clear. And now I would like to go back to the chat, and I think Gabriel posed a question here, which says, could you please explain how the Jacobian works? I understand how to set it up, but I'm unsure every time when I Giovanna, do you want to ask a question? Okay, if you want to ask a question, let me know. Maybe you had your mic unmuted, probably. I'm going back to the question of Gabriel. So, but I'm not sure every time when to use it and how exactly it performs the transformation between 2 spaces. When do I have to use inverted Jacobian? Perfect question. Thank you very much, Gabriel. So, very good question. And I would like to actually also ask colleagues to tell us. We have the, see here, I'm gonna use red. So we have the Jacobian itself, and we also have the inverse of the Jacobian. So I have some questions for you. Could somebody please, oh, this would be actually -1. All right. So could somebody tell me how do we construct the Jacobian? I would rather if you actually unmute yourselves, don't have to type right now. So what's the formula for computing the Jacobian? And when, or before you answer this question, when do we even have a Jacobian? When does the Jacobian even exist? When? Yeah, Giovanna, it's you. Somebody say, please, when do we have a Jacobian even?
I think we have a Jacobian when the parametric size and the physical size change, like the basis vector have to change to describe the one dimension and the other.
Very good. Thank you very much. Let me just reformulate that. So you said that you talked about parameter. This is the keyword here. So we talk about parametric description of a geometry. So I don't know if you heard, but you have 3 ways to describe a geometry. You can describe a geometry, it's called explicitly. So a circle, it's x squared plus y squared is equal to the radius squared. Now this is a way to describe a geometry, and this we call it explicit, right? This is the explicit description of a oh, sorry, this is not explicit. I'm sorry, this is implicit. Okay, that's implicit. What is the explicit? The explicit would be to say for the circle that this is the square root of of r squared minus x squared. So the first one here is a call it implicit this geometry description, and this is a so-called explicit. Which additional way to describe the geometry we have? What is the other one we've seen in the classroom?
The parametric.
Thank you very much. Parametric. Excellent. And how is the parametric geometry description here? It says that x is a function of psi, right? That's the parametric description. And we say, well, that the x of psi is some expression of psi, right? Now, these are three different ways to describe a geometry. Which one are we using when we are performing finite element analysis generally? Parametric, right? We are using the parametric. And why are we using the parametric and not the implicit or the explicit? Who knows why we're using that? Do you remember how we call these elements? I think you may have heard it already in the introduction of finite element analysis, probably. How do we call those elements that we are using? Isoparametric.
Isoparametric.
Perfect. Thank you very much. Isoparametric. So that's the reason why we are using a parametric description of the geometry, because we parameterize our geometry using the basis functions. And the basis functions are already defined in another space, in the parametric space. All right. Now, to the question from Gabriel. Whenever we have a parametric description of a geometry, we have the notion of the Jacobian. The Jacobian doesn't exist if we talk about an implicit or an explicit geometry parameterization, or wrong, geometry description. If we parameterize the geometry with using another space, then we always have a Jacobian, right? That's all. So I just wanted to answer first the question, why and when do we have a Jacobian? Now, obviously, the psi, let's say in the case of the beam, it's running, I'm gonna make an example now. So it's running from 0, let's say, to L, right? That's the physical space. That's my X, let's say. But the psi, it's another space. And this is, if you recall, we always said that this is matching the integration space, the Gaussian integration space. So that space is going to be a little bit smaller or bigger, and it's going to run from -1 to 1. And this is my psi here, right? So now we are answering the question: why do we have a why do we even have a Jacobian? Now, all right. So what does the Jacobian show us now? I will just say it in a very, let's say, very general terms. I'm not going to be very specific right now. The Jacobian shows us how the local space, the parametric space, bends itself to match the physical space. So it's kind of like a measure of change in the length, if you will, for one-dimensional elements, or how to describe the area, the change of the area for two-dimensional elements. That's what the Jacobian actually is basically, thought of. That's the point for the Jacobian here. And yeah, so actually, Gabriel, please let me know if that doesn't make sense. I can explain it more. But again, Jacobian exists only when we have a transformation from a parametric space to a physical space. And to have a transformation from a parametric space to a physical space, we need to have a geometry description which is parametric, obviously, right? Okay, and now the question is, when would we use the Jacobian, and when would we use the inverse of the Jacobian? So please think of it as follows. I'm gonna, there is no more space here, I guess. The easiest thing is I'm gonna start Inkscape. I think that's easier. It's gonna be a white canvas. We are spending some time now on explaining the Jacobian, but I think that's a very important, a very important constituent of understanding generally the method. So it's not, we are not wasting time or so. I think it's important that we all are on the same page here. Well, I was hoping that that's like that the background here is like white, but it's not. Let me see if I can change that real quick. So the background. So where is it? Well, I was hoping to find it easier. Give me please 1 second. How do I move this? I was hoping that this is on the settings. I guess it should be on the settings. Marvel. I don't know which color that is. It's funny, actually. I don't think this is what I'm looking for. Probably it's here. Anyways, I'm going to type like this. So what we typically have to do here is that, firstly, we have to evaluate a derivative of a quantity. Let's call it whatever, u, with respect to the physical space, right? That's the first thing we need to do. And now we know that this quantity, it doesn't matter what it is that it might be the geometry description itself, it might be a field that we try to approximate, whatever. This will always, in the case of the parametric geometry description and the isoparametric elements, this is going to be dependent on the parametric space psi, right? So what do we need here to how can we evaluate this derivative? Actually, can somebody please tell me? We talked about it in the last class, but I think it's important that we repeat that. So how do we evaluate that derivative? Can somebody tell me the formula? It shouldn't be that complicated. It's like one-dimensional here, so it should be easy. And now that's back to the question of Gabriel. Why do we need the Jacobian generally?
I think it was with the inverse of the Jacobian, right? Yes,
thank you very much. Thanks a lot. So also Fabian put it on the chat. Also Surab, thank you very much. So here we have basically the, let me just type it. So this is going to be du over d psi. And then we have a d psi over dx. Sorry, d psi over dx. Yeah, exactly. So what is this here? And that's, Gabriel, the so-called inverse of the Jacobian. All right. Now you see already that to compute the derivative of a field with respect to psi, it's easy because our field is described by means of psi, so it's parametrically described, so it's easy. However, we need to account for this change of length, because if we want to find the derivative of the field with respect to the physical space, we need the derivative with respect to the parametric space times the change in the length, so to speak. That's how it is. And this change in the length is being described by the Jacobian. In this case, we need the inverse, of course, because you see it's d psi over dx, and we need to do dx over d psi to get the Jacobian. That's the first. So that has to do we are using now the inverse of the Jacobian to transform the derivative from the physical space to the parametric space. Where would we need now more the Jacobian? And which other operation? I'm looking in the chat as well to see if you type it there. In which other operation would we need the Jacobian? So we talked about the derivative. What is the counterpart of the derivative of the differential? Integration. Shurab, thank you very much. So now let's say that we have to integrate a quantity integral on the physical space. By the way, we are always integrating on the physical space, right? Not in the parametric space. Our partial differential equation is defined on the physical space. It's not defined on the parametric space. That's why we differentiate on the physical space and we integrate on the physical space. It's important to keep in mind. The challenge we have is that our quantities are not defined on the physical space. They're defined on the parametric space. Why is that? Because we describe them with the basis functions. And the basis functions are defined on the parametric space. So now we have to integrate a quantity u. Let's type this one here, psi. So, and we need to integrate that u of psi in the physical space. How do we do that? Who will tell us? Again, it's a transformation, right? We need to do some transformation, but how does the transformation look like here? Perfect. Surab put it on the chat. So here we have an integral again of I'm not gonna put the space yet here, but it's gonna be u of psi times the determinant of J D. Let's just try to type it here. D xi. And the space we integrate now, it's not. Oh, sorry, I missed it now. You see, it's very hard to type on that. But let me just try to do it again. So real quick. So it's going to be the integral over x of u of xi dx is nothing else but the integral over xi. That's xi now. Of u of xi. The determinant of j times d xi. So what do you see here is that now we need for the integration the determinant of the Jacobian. So for the differentiation, we need the inverse of the Jacobian. For the integration, we need the determinant of the Jacobian. We integrate above equation both sides. Yes, that's right. Thank you, Baba. So yeah, Gabriel, does this answer the question? Do you have still a question on that aspect? Is it clear?
Yeah, thank you.
Perfect. Thank you very much. Great. Okay, so we talked about this. We talked about like the integration, about the parametric description, about like the element parametrization. I hope it's clear that we do not perform any coordinate transformation here. It's not like in Finite Element Methods 1 with the traces. Here, we have one coordinate system, but two spaces. Like there's a difference between a space and a coordinate system, right? I hope that's not very confusing. So in this case, we have a parametrization because we parameterize our element constituents like displacements or rotations or whatever you want in terms of the parametric space of the element. So here is the loop over all the elements. So you will see here, this is how we construct the element, the global stiffness matrix for the two noded linear elements. So here I initialize both the stiffness matrix and the load vector. And afterwards, I have a for loop over all the elements, right? You see, I start from 1 up to the number of the elements. The first thing we do is to get the ID of the element, right? We need to know which element is that. So it's the first, the second, the third, the fourth, whatever. And using the ID, and let me please put a breakpoint here, I'm going to run that. So the ID of the first element is not surprisingly, oh, I'm sorry. Yeah, I was way too quick to speak. Let me please correct myself. So the II is the ID of the element. So this index is called II is 1, right? You see that here. The II in the first iteration is equal to 1. Okay, and now what is this ID? Basically, I go for each element here and I request all the IDs of the nodes that belong to that element. Hopefully, it's not very confusing. So let's say, for example, that you have here. Okay. Let me think. Why is that like this? Let's try to see that. It's going to be all right. 3 nodes here, basically. Now I confuse myself actually because let me. I don't know why I have. Maybe somebody can actually help me. So I don't know why I have 3 IDs here. I should have had 2, right? I don't know where I have. Maybe I'm in the quadratic ones or something. Oh yeah, I'm in the quadratic ones, of course. So you see here, I have somewhere a mistake. Why did I call it? All right, so you see, yeah. So when I call it here, let me just zoom in again. I'm sorry for that. The mesh is called mesh L2, which means like quadratic, right? 2 means second order, right? Second order. I'm sorry for this. So I was looking at the quadratic ones and I saw the IDs and I have 3 IDs per element. So how is it possible for a 2-noded linear element to have 3 IDs? I was confused. So I have to scroll up and go to my quadratic ones and put the breakpoint here. And I'm going to run again the loop, so you can actually go to the run section up here in MATLAB, so you can just run the run section button. Two, which means like the first and the second element node, sorry. So basically here we have, that's pretty straightforward basically, because you have a mesh which looks like this, and that's the first node, that's the second node, that's the first element. So the first element comprises out of node 1 and node 2. The third element will comprise of, here's going to be element 2, and this is going to be node 3. What is gonna, which nodes belong to the element 2? Based on the sketch that I have here. Yes, which numbers? Okay, thank you. So 2 and 3, exactly. So the second and the third, 2 and 3. So if I just run the loop, go to the next loop, I'm gonna say continue. Oh yeah, continue again. So we're gonna see now that the ID is gonna be 2 and 3. Great. Now I'm using these IDs here in the nodes. So I go to the nodes and I provide this ID. So you see MATLAB is quite nice in this. You can provide, you can index an array, So nodes itself is already an array. So if you see the nodes is already an array of 31 elements, it's like a column vector basically. And we say we want the second and the third element. So the nodes I mean, if I show you this, already you can tell that the second and third elements are these two, right? These two things here. And so that's exactly what it is. If I put my cursor here, you will see that that's exactly the two numbers. And now I have basically the description of my basis functions. Please note that in a symbolic form. That's the one, that's the n1, and that's the n2. And I have it in a vector. I pass them into this function here, the compute element, stiffness matrix, and so on and so forth that I showed you before. I also pass the nodes. I'm actually interested about the nodal coordinates. And lastly, I'm also passing. So now I'm going to basically say continue from the button up here. And we're going to go into the implementation of the matrix itself. And now it gets interesting. So you see, I'm using again symbolic math. So I'm gonna, you can use the step up here if you want to move line to line, the step up here, or you can press on your keyboard the F10 button. So the F10 key, sorry, is gonna move me line by line. So now we have the XL. That's nothing else but so what I'm typing here, X is equal to N times XL. Let's look at this. So the N is the two shape functions or basis functions, the ones that we've seen before, and the XL, it's just a symbolic way to write the two nodes from the element, because I wanted to formulate it in a more general manner, so that it's not particular to one element, so it's more easy, or it's more comprehensive in a way. Now, if I make this multiplication, I'm going to press on F10. You will see that the X now, it has an expression, right? It has this expression here. It's the second node of the element times the base function, the second base function, minus the first node times the first base function. So that's nothing else but N1 times psi. Oh, let me just try to type it differently. I didn't like this. Again, so this is going to be, I tell you this N2 actually, and this N1. MATLAB is sorting them like this, doesn't matter, it's the same thing. And now what the description that I have is that X of psi is equal to N1 of, it's a very hard life without an iPad, I can tell you. For you, it's also not a great experience right now. I'm really sorry for that. Let's try that again. times x1 plus n2 of psi times x2. That's exactly the expression I wrote here, and that's exactly the parametric description of the geometry for isoparametric elements in that case, right? So we have this formulation in MATLAB now already in symbolic form, which is great. It's great to have a symbolic form because we can actually differentiate using function diff, or we can integrate using function int. So MATLAB gives us these functions that we don't need to bother ourselves, doing the integrations and the differentiations ourselves. So if we now I'm going to proceed to the next lines. I get here the polynomial degree, then I get the number of the elements, those degrees of freedom per element, which is that 2 times the number of the nodes, because we have a vertical deflection and a cross-sectional rotation for each of the nodes. And now we set up the Jacobian. Now, of course, I mean, it's super easy, right? You can take this expression and integrate it yourselves. Like this is straightforward. However, if you're going to quadratic or cubic elements, it becomes cumbersome. So to differentiate, it takes you a little bit of time. So why not using MATLAB or any other symbolic symbolic math software, basically, if you will, to actually differentiate, let the software differentiate it for you. You don't need to do it yourselves. So in this case, I have the function Jacobian. It comes from the symbolic math toolbox. That's a built-in function in MATLAB, as I said, symbolic math. And you just provide here x, which is a symbolic function, the parameter for with respect to which you would like to differentiate, and then just call the Jacobian function, and you get the Jacobian. So I'm sorry. Before I compute the Jacobian, can somebody tell me, will the Jacobian be in this case constant or non-constant? What do you think? I mean, let's put the cursor again over x. Minus x1 divided by 2. So x2 and x1 are constants. These are the nodal coordinates divided by 2. So that's constant, right? Is it clear to everybody? Hopefully it's clear. Any questions on that? If you have any questions, unmute yourselves and ask. All right, but that's honestly uninteresting, right? I mean, it's a constant Jacobian. It's like everything is simple here. Let's stop the debugging mode in MATLAB, and let me just go. I'm gonna go all the way up to the table of contents, and I'm gonna go instead. Now I was in the 2 dimensions, like you see, I was before here. Let's see, I was here, which is the master stiffness matrix and load vector for the 2-noded linear mesh. I'm going to go now to the master stiffness matrix and load vector for the 3-noded quadratic mesh here. So you just click on the hyperlink, and we are now there. Now I'm going to do the same thing as before. I have still a breakpoint for the debug mode in MATLAB already in the function. So I'm going to say run section, and it's going to bring me back into the function that I was before. And I'm going to press again step, and again step, again step, and last one more time to proceed. And now I'm going to check out the x. What is x? I'm sorry. So you see x now is no longer constant. Sorry, it's no longer linear. I mean, it's a quadratic element, right? So it's not a surprise. So if I just zoom in here, you see I have x or psi times psi, psi times psi, and again, and we have an expression that contains psi again. Could you please, Fabian, I'm going to come to your question. Can somebody tell me which function is that? Remembering from the last in-person practical lab session, which one is this? Ah, perfect. So I'm thinking the bubble. Remember, this is a nice bubble. So if we had here the three, let me just try to make a mesh with a 3-noded quadratic element. So, and I'm going to use red. That's going to be that function here, the bubble. All right, that's a bubble here. Great. Fabian is asking, can a 2-noded element have a Jacobian that isn't constant? That's a very good question. And I would like to actually throw it back to all of you. Let's say I have a 2-noded element, right? Which which functions are we using to construct the basis functions? Do you remember the name of the functions we're using to construct the basis functions we had in the first lecture? Just put it on the chat. Or no, hat is just a nickname. It's not a proper name. Hat is just like because they look like hats. I need another name. You remember the polynomials we were using to construct them? No, bubble is the one we see here. Which functions were we using to construct the basis functions? We had the name for them.
Lagrange.
Lagrange polynomials. Thank you very much. Excellent. So that is the Lagrange polynomials. And what is the order of the Lagrange polynomials? What does the order of the Lagrange polynomials depend on? Do you remember? So let's say, like Fabian is asked, excellent, thank you, Alexis. So it's points minus 1. So Fabian, the question to you now. How many points does, exactly, thank you very much. How many points does the two-noded element have? It has, okay, great, so you got it, thanks. So exactly, it's first order. It's because we're using the Lagrange polynomials. Now, if you come up with another, or not you, but generally, if we come up with another set of polynomials that, you know, they use a higher order for the using they leverage two nodes to construct a higher order polynomial, then we can get a higher order polynomial based functions, and then we can actually have a non-constant Jacobian. But because we're using the Lagrange polynomials, we are confined here. But it's not let's say impossible, right? It depends on the way we construct the polynomials. If you had, for example, the Hermite polynomials, or I think the Hermite polynomial is a good example. So those are cubic. They need two nodes also, and there you could get like a higher order polynomial. But then you can also go to isogeometric elements where you don't have any more interpolation. No, the thing is the interpolation makes us a little bit like confined, right? Because we need to interpolate two nodes, and to interpolate two nodes, we need to use like the general rule says the straight line passes through uniquely through two nodes. If you have like a parabola or something like a quadratic polynomial, this does not uniquely, it cannot be uniquely described by two nodes, right? So you can have an infinite number of parabolas that can pass through two nodes. That's why we're not using that, because otherwise our stiffness matrix would have been singular. Whenever you hear infinite amount of polynomials that can actually be used to describe or to interpolate two nodes or more, it means immediately that our stiffness matrix eventually is going to become singular. Hopefully that answers the question. We still have 10 minutes, and I would like to go through the workflow all the way to the end. So here I'm going to proceed with the step. Where is it? Step. We get the number of the nodes. Then we get the Jacobian. So now the Jacobian, let's see how it looks like. So it's going to be obviously non-constant. Right. You see that here is already a function of psi. However, that's constant. So if I were now, let's go to MATLAB. Let's do a game on my workspace, right? If I take now this J, you see the expression on the command output window. I'm going to maximize that. Right here, I take the derivative of the Jacobian with respect to psi. Now that's actually constant, right? So you see that although the Jacobian is not constant, it's actually linear. So the derivative of the Jacobian is going to be constant, right? Let's go back here. And now the question that Gabriel had before. Now, please take a look here. We want to compute the derivatives of the basis functions with respect to the physical space. And now again, why do we want to do this? Because let's go back to our script here. If we look at our partial differential equation, where is it here? Well, that's the weak form here. So you will see that we have a derivative of the vertical deflection with respect to physical space. Now, this apostrophe in the script, it means that that's a derivative with respect to the physical space. So that's actually nothing else but the variation of the derivative of W with respect to X. And the same thing holds for the betas. So our variation formulation contains derivatives with respect to the physical space. Thus, we need to actually compute derivatives with respect to physical space. And therefore, in here, you will see that I'm taking the basis functions now, and using the Jacobian, I'm constructing the derivatives with respect to the physical space using the derivatives with respect to the parametric space. So if I actually zoom in here, please let me know if you have any questions. But this expression here, the diff of n with respect to psi, is nothing else but a d. Ah, my God, this is terrible. I need to type it. So this is a d n with respect to d psi. Okay, that's what it is. That expression here, this one. And afterwards, the expression we compute out here, that's actually dn dx, right? So you see, we're using the Jacobian here. We actually use the inverse of the Jacobian because you see the backslash operator in MATLAB, which means like inversion of the inverting a system to compute the physical derivatives using the parametric derivatives. Any questions here are more than welcome if you have any. Good, and then it's actually straightforward. So if I proceed with the stepping in, and I compute here, you will see the so-called material matrix, the C. So I'm just stepping in here. I'm stepping in that, and let me put them together. So you see, it's actually the same thing. So the material matrix here is, where is it? We talk about the let me find it. I hope that it's written somewhere on the notes. I was thinking that it's written somewhere. Here it is. So you will see that it's here. So that matrix here is literally that, right? I guess everybody can tell that. And then we construct the shape function matrix. I'm gonna put a breakpoint here, and I'm gonna run it up to there. We'll remove the breakpoint, and let me see, where is it? These are the three noded elements, right? So here you see the base. I'm gonna bring my cursor over the n. We get that, and now I'm gonna zoom in. No, and this is the basis function matrix, which is actually the same as this one here. Who can tell the difference, please? Does anybody, can anybody tell the difference here between the two? Yeah, exactly. Thank you, Alexis. So there is actually there is an additional basis function. I mean, we have here also the n3. So this is an n3, and this here an n3, and that's because we are using in the script. I just run the quadratic ones, right? And in the computational script, in the static PDF, we only the script only contains the two noded elements. I use also exactly the third ones, right? So it's the same thing. If you have a quartic or like quintic or whatever else, this matrix just carries on expanding. It's like no difference, right? It's carrying on expanding. That's it, basically. It's straightforward. And then I'm computing the B operator matrix here. I'm doing some interesting matrix indexing of matrices here, which is not very complicated. I'm going to put a breakpoint at the 229 line, run it up to there, and I'm going to bring the cursor over the BTX. And now I'm going to again highlight that, so you see. Sorry, I need to scroll so you see more clear. So let's try that again. So let's see here. Okay, now you see the B operator matrix is this expression here, and that's exactly again this one, right? So this expression that you have on the script. Again, you have one additional shape function because we are having here the quadratic ones. At least I'm demonstrating the quadratic ones, but I hope you can tell it's the same thing. And you have the zeros here in the place where you expect them to be. Like, okay, there's the zero there also as well. And yeah, again, the derivatives of the base functions you see on the B operator matrix are with respect to the physical space. You see comma x. It's not comma xi, it's comma x. Okay, and now we have an expression of the B operator matrix in the parametric space, xi. Now, to compute the integration, you have the option here to use the drop-down list. So you can say, I want to integrate over the physical space. I want to integrate over the parametric space, parent space. When I say parent space, I mean the parametric space. I'm really sorry for this. Is another word, a new word for the vocabulary of the finite element methods. When we say parent space, typically we mean the space where the integration takes. Parent space means the parametric space, but not the integration space. In our case, integration space is the same as the parametric space. So when I say parent space, please keep it in your minds the same way. And you can say parent space, then you can say parent space using Gaussian integration, or integration over the parent space using selective reduced Gaussian integration. Now, the last option here, it will be interesting in the lectures to come. We're going to talk about the transversal locking. Right now, we're still concerned ourselves with the element formulation in general. We don't talk about numerical issues like transversal locking or whatever. But I would like to motivate you, actually. I will use the physical, or let me think. I'm going to use the parent space. So I'm going to choose here parent space. I chose it already, hopefully. Whenever you change the selection here, the whole script runs from the beginning, by the way, so you know. So now it's run the whole computational script from the beginning. I set it up like this so that it makes more sense. You cannot just change the variable in the middle of the computations here. Otherwise, it would get you an error. So now I changed it to the parent space, which means the parametric space, right? The integration. And you see afterwards, I have a switch, a MATLAB switch branch, which tells, well, if it's like the first, second, third option or whatever, it takes a few seconds because I'm plotting the basis functions. Actually, that takes the most of the time. The script itself is relatively fast. It's just like when I'm plotting the basis functions, it takes longer because I'm using symbolic stuff. So bear with me for a second here. Hopefully it's going to be finished very soon. I think we're stuck now here. Yeah, there we are. We are stuck here, actually. You know what I'm going to do? I'm actually going to stop it because I don't want this visualization. You know, like you can also play the video here, see all the base functions for each element, which is quite cool. But I don't want to plot it, actually. So I need to comment these lines of code out because I don't want to plot that. And I'm going to run it again, and it's going to be much faster now. Because it takes, as I said, I'm plotting symbolically each function for each element. We'll have a lot of elements here, so it takes some time. So this one probably won't take that long. And now I'm expecting to, oh, where's the break? I missed the breakpoint. Ah, it's here, okay. Integration over the parent space. Okay, so you can open the drop down list and see where the integration takes place. I want to show the parent space, and I want to use the quadratic elements. That's for me the most interesting. So that's here. So I'm going to run that section. It's going to stop here. I'm going to play the continue button and then come here. So now you will see in this place of the script that you have a integrand for the stiffness matrix and for the load vector. And if you bring the cursor, please do that. If you're open, if you have your laptops open with you there, I mean, not laptop, sorry. If you have the courseware open, please try to reproduce the workflow. And if you bring the cursor over these variables, you will see that that's actually the global stiffness matrix. It's already, let me think. No, what did I say? This is not the global. This is like the local one, obviously. And it is formed symbolically, right? So you see this is a symbolic formulation. And you will see that actually it uses here sigma 1, which are some sub-variables, and they're defined afterwards. For the sake of compactness here, MATLAB is trying to make it as readable as possible. So it takes big expressions and formulates like sub-expressions, which is useful for you to be able to tell, okay, that's my element stiffness matrix here. And the same thing with the load vector, but that's a vector, obviously. And now, since we use the integration method to be the parent space, you will go to the switch method here, integration method, and it's going to test for case 0. It's not the case 0. The case 1, it's the case 1. And now we are using in MATLAB the function int. And please, let's go back to the question from Gabriel. You see here what I'm doing. I'm actually integrating in the parametric space, psi, from -1 to 1, right? Because that's my parametric space. And now I take my integrand that I formulated before, and I multiply that with the determinant of the Jacobian here, right? And now I let MATLAB do the integration for me. So MATLAB does the integration for me. By the way, MATLAB is not using Gauss integration. I just want to show you that I just want you to understand the symbolic expression of the stiffness matrix and the load vector. That's all I want you to understand. And MATLAB has functions for the numerical integration, like the int in this case, but you see it takes a long time because it does not use Gauss integration. The Gauss integration is the most efficient one for finite element methods. So in this case, please bear and don't use the parent space because you see even for one element, it takes really long to compute. Again, it doesn't leverage the Gauss integration. That's the reason why. but it does automatically the integration for you. So we need to provide here the integrand times the determinant of the Jacobian and the space where we integrate, which is basically the -1 space, because that's my parent, that's our parent space here, psi. It runs from -1 to 1. Right, and let's see, it's still running. So again, as I told you, right, that's the quadratic elements. That's why it takes also longer. For the linear elements, will take much quicker. But yeah, that's hopefully. I mean, you will see also when you run yourselves, it takes a long time, so you don't need that. So on the case 2 is the integration using the Gauss integration, and you will see that I have coded this Gauss integration myself, and you will also need to learn how to code that because you need to solve the exercises. So actually, what I want to say is that to solve the exercises for this week, this is all you need to know. There is no more than that. Any questions? So we are over time now, 2 minutes. But I think I went through everything I want to talk to you today about. Just want to make sure that you understand how the MATLAB syntax works for this particular formulation. I think if you get it, like if you familiarize yourselves with that, going to the Reisner-Mindlin plate is not a big deal. It's actually relatively easy. It's just like the ordering of the shape function is different. Yeah, but well, that's I would say all for today. But I'm gonna stay here if you have any questions. So I'm gonna stay another 10 minutes here. I'm gonna answer possible questions you may have. And of course, I'm gonna upload this recording afterwards on Moodle as we do every week. So I'm gonna the recording. I'm gonna process it a little bit to remove some parts that are noise, and then I'm gonna upload it on Moodle. And otherwise, thank you very much for joining, even so early at 8 o'clock in the morning.
Yeah, sorry, I had a question about the MATLAB scripts.
Yeah.
Because I struggle to run them every time. Maybe I can share my screen.
You can do that. Please go ahead.
Yeah. Yeah. So if I run the script, I always get this error.
Yes. Double click on that first. Say open. So that's a project file, and it sets all the dependencies. It initializes variables that are needed, like auxiliary variables. And once it is done, just wait for a few seconds to finish. And I think it's still configuring the environment. Interestingly, it takes longer than I expected it to be.
Okay.
Yeah, I think you can actually close it, I believe. I suppose from the I think. And now, can you please try to run that again? The script, yeah.
Oh, okay.
Yeah. So it's just because I have the functions in some folders, and you need to set up the environment for it to run. So that's a good question, though. Thanks.
Yep. Thank you.
Absolutely. So please feel free to either leave the chat, or if you stay, you can also ask me questions. As I said, I'm going to stay for another 5 minutes here.
Herr Bletzinger always talks about the integral over the bending part and then the integral over the shear part for the Reisner-Mindlin plate, for example. But when we did when we should do the B matrix in Moodle, it was the other way around, right? It was the first row was for the shear part because we have the form function derived, and then the normal form function. And that's like just another way to this another It's other way. It's first the shear part and then the bending part, right? That's the only difference.
Yeah, it's so basically there is no difference in the order you integrate them, because integration is like it's what's it called? It's an operation that can be reversed. Not reversed, sorry. I forgot the English word for that now. You can change the order, right? So you can. It doesn't matter if you sum up first, so it's the same thing. But it will play a role for us. So we will see in the next lectures. It plays a role to integrate those two parts, the burning and the shear part, separately, because we need to address this transversal locking. So we're gonna see later why it's necessary to do that. So I believe Professor Bletzinger probably did the same in this lecture, if I'm not mistaken. But yeah, you can change the order of performing the computing the stiffness matrices there for the individual parts. There's no difference.
So the matrix for the B operator can also be like 0, N1, 0, N2, and then on the second row, the derivative N1, N1, derivative N2, for example.
Yes, absolutely. It doesn't matter. It's what you said. Is the ordering of the degrees of freedom, probably, right?
Mm-hmm.
So the way I order them is probably different than from what you tell me. I don't know the lecture notes from Professor Bletzinger, but I believe probably he's ordering the degrees of freedom differently, and that's what. But it's really just a matter of ordering.
Okay, no, because the matrix looks the same in the script, but when he writes it down in the script, he always puts first the bending part and then the shear part.
Okay. It doesn't have to do with the degrees of freedom. It has to do only with the way the sequence of computing the different matrices.
Mm-hmm.
Okay, there is no difference. Absolutely no difference. So you can compute first the bending or after. It doesn't matter. As you see, there's a plus symbol in the middle, so it's actually a summation.
Yeah. Because I was confused because I did it the wrong way around in Moodle, and then after trying it and changing, it worked perfectly.
Oh, I see. Could you please write me an email for this, because I would like to check it out myself and then maybe make it compliant with what Professor Bletzinger has, so that the students are not confused. So if you can write me an email and tell me exactly what you did, so or send me your solution ID. Perfect. Thank you.
Because I also want to be in this Übungs thing of MATLAB, then I also have to write.
Perfect. Awesome. Great. Thank you.
All right. Thanks.
Awesome.